safety strategy with all these components. Now, this is where the failure happened, okay? So where the failure happened here was that they constructed the fire safety strategy, but they didn't realize the dependencies and the conflicts that were being created, so they didn't really understand well how the building worked. So in essence, if you look at this, basically you're going to have redundancies because you're going to put multiple detectors. So if one detector fails, there will be another one that picks it up, okay? So this one has a lot of redundancies. Obviously, the compartmentation is 4 levels of redundancy, okay? Now, the fire brigade will be the redundancy to the entire building safety. So if the building doesn't operate correctly, I have the redundancy that the firefighters will come in and be the cavalry in a way, okay? Now, the structure is designed for burnout, okay? So all structural components, the methods of design that we use are such that the concept of what we call fire resistance is the design for burnout, okay? So it's extremely conservative because you can consume all the fuel in the compartment and the structure will still be in place and it will be fulfilling its function entirely. So we have a lot of conservatism in here that acts as a redundancy. Now, the problem is the no external fire spread because it creates dependencies. So if it spreads externally, it bypasses all the compartmentation and it affects the people above immediately. Now, it has a dependency because when we design a structure for total burnout, we are assuming that the fire stays in one compartment. So the fuel that is burning is the fuel within one compartment. So if I miss this and I start heating from both sides, then the conservatism is gone. So Grenfell Tower is cracked in half. So if you go past the 7th or 8th floor, the concrete slab has something like 5 centimeter gap. So it has to be propped to be kept in place because the building is actually splitting. Because structurally, it withstood a load that was much more than what it was designed for. On top of that, if the fire spreads, then people cannot stay put because then the fire is affecting multiple units and it's not possible to keep people in place. You have to try to get them out. But unfortunately, you've created a dependency with the firefighters because they came in with provisions to fight a 1-unit fire, okay? And not only that, but you created a conflict because you gave them priority, which basically meant that they will take over the stairs and allow the stairs to fill up with smoke. So once that happens, then you cannot revoke the stay put strategy because people will have to walk into a stair full of smoke. So by not doing the complete analysis, effectively you've created a single point failure mode. This is a perfect Swiss cheese example where all the holes have aligned and literally you have a single failure mode that dismantles the entire building, okay? So in essence, then the importance of understanding external fire spread becomes critical for this building. Now, in other buildings, you might have other provisions that are put in a certain way that don't create the same level of dependencies on one single component of the strategy. But in Grenfell, effectively, if you missed the external fire spread, everything falls apart. And that's exactly what happened, okay? So what is the role of combustion in defining adequate fire safety? It helps us create regulations. So if you understand the combustion process properly, you can regulate properly, okay? Because you understand what needs to be put in those regulations to be able to do things correctly. So fire safety is a very complicated problem that has an enormous social importance. And because it has that, it has to be very heavily regulated. Okay? And regulations can be of 2 types. They can be prescriptive, where you have fixed rules that you have to follow, or they can be functional requirements or performance. And fire safety nowadays is mostly in the performance space, where you have very high societal importance and you have very complex problems that cannot be done but with rules because the products are entering the market too fast. So by the time we actually change building regulations, we've already been invaded with a dozen new products. So we don't have time to remain in a prescriptive world, and we're moving very much to performance. The simplicity that comes with prescription of the common building is something that we don't have the privilege anymore. So in essence, fire safety is complex and important problem, and basically it impacts a very large number of people. So we have to regulate people to actually do the job properly and allow them the flexibility to use performance-based design to be able to do the job properly. Now, I said I was going to use the British system to illustrate how that is done. Okay? Now, it's pretty straightforward because effectively the British system, the entire building regulations pertaining fire in the British system has one page, and it's this page here. That's a requirement. It says an engineer has to develop appropriate means of warning and escape, B1. Internal fire spread has to be managed so that it's appropriate, B2. Internal fire spread, the design of the structure has to be done correctly, that's B3. The external fire spread has to be done correctly, that's B4. And you have to give the firefighters everything they need, B5. That's it. Everything else is the responsibility of the professional. And the detail is described in these terms. So for example, when you're talking about external fire spread, it says the external walls of the building shall adequately resist the spread of a fire. Now, it's a completely ambiguous term, no? What does adequate mean? Only a competent professional that understands whether it is 5 minutes, 8 minutes, or is infinity, is going to be able to define this. And it has to be done having regards to the height, use, and position of the building. So basically, in your design, you have to consider all these things. So that type of design approach basically puts all the weight on competency. Now, the way it's implemented, it requires for the engineer to set up the objectives, as I said, then construct a fire safety strategy, as we discussed, and that fire safety strategy is what is deemed compliant. Okay? And basically, the requirement has to consider all these 5 points, and you provide also all sorts of guidance. But this is just guidance. So you give some common solutions for people to have a reference point where to start, but you decide whether it is applicable or is the appropriate approach, or you're going to use different tools to do that. Okay? But in essence, you are defining the overall objectives and the fire safety strategy. You are defining the professional boundaries because you have to know when you interact with the structural engineer, when you interact with the facade designer, when you talk to the architect, and therefore the responsibilities are also defined by the professional. That's a true functional requirement system. Now, of course, if people that are doing this are incompetent, okay, the whole system falls apart. And that's the problem of the British system, that effectively, in the absence of a proper definition of competency, the system falls apart. So, because it places an enormous emphasis on professional competency. So, we regulate to allow for competent practice, okay? Now, as I say, in other countries, you have much more restrictive systems that are purely prescriptive or very prescriptive, like in the US. China is the same. Australia is more functional requirements. New Zealand, more functional requirements. Mostly the British colonies tend to be most functional requirements. Germany is very prescriptive. France is moving towards functional requirements. In other countries, they allow the two systems to coexist. For example, in Spain, you have prescriptive regulations, but the option of doing it in performance. So you have all sorts of variants of this. So the regulatory mechanisms, so this is a problem. Okay? Because if you look at those two buildings, you have to decide which one is more complex. And the reality is that it's not trivial. There's many, many, many details that will actually change the complexity of the buildings. So for example, if I look at this one, basically it's all glazing. So if the glass breaks, the fire can move all over the place. That's the complexity of this building. Well, the complexity of this building is hidden because the building is made out of mass timber. okay? And that sets a whole other set of rules in regards, to the problem. And I say that the two approaches are performance-based or functional requirements, where it's all about objectives, and there is no classification of the building. It's the professional who does the analysis and delivers the solution. While in the case of prescriptive solutions, you classify the building. You say, this building is an office building. And you iterate 1,000,000 times until you get the solution right. You set up a whole set of rules, and you write them in black and white, and you have to respect them like a recipe, okay? And that's NFPA. So, and the nature, obviously, of competency for all this is very different. And, of course, compliance is the dialogue between the designer of the building and the approvals officer, so the two of them have to be competent. Because if not, you're in trouble. So this is a problem of lack of competency, okay? So if you, in the case of a building design, you're going to have an authority, you're going to have, obviously the fire service has to be involved because it's their workplace, and you have the designer, okay? Now, if everybody's competent, everything works. The moment that one party is not competent, then you get diminished results. But if the authority is incompetent, inevitably, you have the worst possible outcome, okay? And in most countries, this is what the big problem is. Why? Because the authority has to supervise a multiple set of disciplines, so they cannot be experts. And it's the experts that have to translate the information in a way such that becomes tractable to this. So this is a Notre Dame problem, okay? So at the end, fire safety is mostly, about competence that needs to be regulating, and really regulating the person is what is important. So, and this is the problem that we have, that currently we have a lot of inconsistencies. So let me show you the conclusions of the Grenfell Tower inquiry, okay? So this individual is called Richard Millett and is the lead counsel for the inquiry. And this was his closing statements before they went to write the report. So that was the last statement that they made, okay? So basically he said that that morning, the owner of the building was the first one to call the fire brigade. Why was that important? Because the occupant did his job. The only responsibility the occupant has is to get out and call the fire service, okay? So by saying so, he exempted the occupant from any responsibility. Then he said, from all the evidence that you have heard, you are able to distill a single overarching conclusion, that there was nothing unknown or not reasonably knowable which caused or contributed to the fire and its consequences. What does that mean? We have the knowledge. The knowledge is available, okay? And we could have designed that building properly because we have the knowledge to be able to do it. Now, he says, on the contrary, each and every one of the risks with eventuated at Grenfell Tower on that night were very well known and ought to have been known to all who had a party to play. Now, that is a really powerful statement because it means negligence. The knowledge exists, you should have known, but you didn't, okay? And that is the highest level of charges that professional practice can have, which is that you acted negligently, okay? So then he says, as a result, you will be able to conclude with confidence that each and every one of the deaths that occur in Grenfell Tower was avoidable. So in other words, your negligence is the responsible for killing 72 people. So basically, that's manslaughter, okay? And so it's an extraordinary charge, yeah.
An interesting aside, at least in the United States, an expert is supposed to be acquainted with the research literature,
yep,
as well as the established document.
Absolutely.
You can't say that this was research material and I didn't have to know it.
Yeah. No, basically you have to be acquainted with the state of the art. That's the level of professional practice that is expected. So then the final conclusion then is a litany of incompetence, poor practices, dishonest practice, weak and incompetent, failure to central government to act despite known risks, failures of competence, training and oversight. So basically, everybody's incompetent. That was the result of the whole inquiry. That building was designed by a whole bunch of incompetent people that didn't really understand what they were doing, okay? It was so bad, this was in the front page of all the newspapers. This is what he called the web of blame. They're so incompetent that they didn't even understand their own responsibilities. And through their testimony, every one of the parties, all they did was point finger at the other. And every arrow represents who accused who. And these are all the parties that were involved in the design and build of the building. No, not a problem. Okay, so if you think about it, if you have a low budget, effectively, you hire the cheapest architect, unnamed. You have hired the cheapest engineer. You give them a very low budget, so they do a very simple job. I mean, in this case, the engineer that was in charge of designing the facade system was a 22-year-old, and this was his first job out of college. And of course, it was the cheapest thing that they could possibly put in place. The design, in principle, is meant to be standardized, so the authorities pay no attention. So the approvals process is done in a very summary way. Now, if you're designing this building, then who do you hire? So Rafael Vignoli, everybody has a name. This is a star architect, who designed these amazing buildings. And you design, Irving Cantor is one of the leading structural engineers designing super tall buildings. And everybody, is a leading person. And as a result, you have a unique design. And of course, because a unique design, that makes the authorities nervous. So they put a lot of effort in trying to make sure it's okay. And as a result, you get a safe building. So basically, it is social inequity by legislation. And that's what you've created. And this is really, a big problem. So we failed to meet society's expectations. We render ourselves incompetent. We lost trust. And now we're in a position where we have to try to recover that. So, and this is a reality of people not engaging in this profession. Remember at the beginning, what I said was that somehow combustion science withdrew, from fire safety. And we need to recover that space because this has brought us into a position in which actually combustion science affects every decision that we make, but nevertheless, we don't have the people in place. And the reality is that unfortunately, the combustion scientists, that many of them go into fire, they're not very well versed on the fire aspects of the problem. And this is why I felt it was so important to give you this broad introduction before we get into the details of the combustion problems that you need to address. Because if you don't have the context of fire, fire is not a problem that can exist in isolation from its boundary conditions. The boundary conditions define the need, and as such, you need to understand them to be able to understand what knowledge you need to have. So, what we should have known, and is there a role for combustion science? Absolutely, it is 100% a combustion problem. And it starts just by simply being able to define what is the difference of a fire outside and a fire inside. So if you look at this, what are the characteristics of the combustion processes in a compartment where you have restricted ventilation and radiative feedback from the walls back into the fire, as opposed to what is a fire that actually spills out to the outside? The two are completely different boundary conditions. Now, if you look at it from a really fundamental perspective, you will realize how different they are and what is the things that you really need to know. So, for example, when you are inside, effectively you get a fire that spreads, it starts heating up the ceiling, then you get radiative feedback, eventually you ignite all the components, and this fire becomes ventilation limited. What does it mean? That you have too much fuel, and you have to break out through the windows to get oxygen coming in, through the windows. Now, that leads to temperatures or heat fluxes of the order of 400 kilowatts per meter squared, which is completely different to what you will get in a fire that spills outside. Now, in a fire that spills outside, you need to be able to model these turbulent flames and establish how far they're going to heat up. So you need to be able to predict what is going to be the flame length, in as much as you need to be able to predict how much heat flux goes back into the material that potentially could be ignited in the case of polyethylene. Now, you will look at now the different heat fluxes, and you will realize that they follow a decay function, but that decay function has a maximum of about 60, as opposed to 500 inside. So in is completely different than out. And we need to be able to understand why we get much lower heat fluxes on the outside than we get on the inside, and how these heat fluxes, for example, can ignite a fire in another building as an external heat flux, fires from building to building, which is a huge problem nowadays. It's a problem that we had solved in the past by creating separation between buildings, but those separations were predicated on a single floor fire. But now that we are allowing these facades to create multiple floor fires, now we have a problem with what is the external heat flux that goes from one building to another building. And that, again, is a completely different problem with a completely different order of magnitude. Now, the spread problem, so this is the vertical flame spread problem. If I simply used a material that is homogeneous and it's burning, where you're going to have a region of pyrolysis that is going to produce pyrolysis gases as fuel vapor. Now, at the end of pyrolysis, part of it is going to be consumed in the diffusion flame, but part of it is going to leave to create this flame length. This we normally call excess pyrolysis, and is going to extend the flame beyond the area of pyrolysis. So this LH here, if it is greater than 0, allows for the flame to spread. While if this LH approaches 0, then that basically means that the flame stops spreading, okay? So the preheating region here, which is heated by the flame that is supported by the excess pyrolysis, is the one that actually determines whether the flame is going to spread or not. And that is going to change whether you have an external heat flux or not, okay? An additional supply of heat. So we'll look into this problem and the characteristics of how it is quantified. But effectively, even if I just take a simple combustible material, this in itself is an extraordinarily complex problem. About a couple of weeks ago, there was a Professor Fernandez Pello from the University of California, Berkeley. He is probably the most eminent person when it comes to flame spread. And he was asked to give a review paper on flame spread. And he started by saying that, I mean, he's in his early 80s now. And he started by saying that he had dedicated his entire career to flame spread. And he had come up to a conclusion that he had achieved nothing. And because they still couldn't understand even the very basic principles of how vertical flame spread occurs. But I'll try to explain, how it works. But the one thing that is interesting about vertical flame spread is that it's such a complicated problem. But if you actually isolate some key variables, you can actually predict things in a very conservative way. So being able to identify the key parameters that control the problem actually allows you to quantify conservatively what the spread rate is going to be. And you will have to design conservatively until we actually solve things correctly. Now, one of the key problems in vertical flame spread is establishing the flame length, because at the trailing edge, and this is a characteristic of diffusion flames, which is a different form of strain. We normally think of strain as basically created by velocities that effectively create, a shear space that basically stretches the flame and leads to extinction. Now, there's another form of strain, which is when the fuel is arriving so slowly that effectively the flame temperature starts dropping because you're creating less energy because of lack of fuel. So as you progress away from the fuel source, then what happens is that the temperature of the flame starts dropping until you get to quenching. And basically you get this sort of low velocity strain that leads to quenching at the trailing edge, and that's what defines the flame length. And this is why all these fire problems will always have a lot of smoke coming out, because you have a lot of unburned fuel, because quenching is what limits the problem. So effectively, the critical aspect of flame spread is being able to quantify the flame length, quantify the pyrolysis length. The difference between the two of them, flame length and pyrolysis length, is the preheating region. And that preheating region is the one that has to ignite. And we need to be able to quantify the ignition delay time in such a way that length over time gives me velocity, okay? Now, this ignition delay time depends on the energy balance, and as you can tell from all the million arrows that I put in here, this is not a trivial problem to solve, and it needs to be characterized in an effective way. This is a combustion problem, okay? So now think of reality. Now it's not a single material, but it's all these very complicated composites with all these different layers that we need to be able to address to be able to characterize, the spread of the flame. Not only that, we're going to put it in a configuration where we're going to create radiative feedback by creating a cavity. These ventilated cavities, again, are done for purposes of energy consumption reduction and prevention of mold. It has all sorts of functionalities, but create a problem that now becomes much more complex, that has two different types of flows, which is the channel flow and the external flow. You're going to have another flow, which is melting. You're going to have burnout, because of charring, which creates a complex chemical kinetics problem associated to pyrolysis, as well as a whole bunch of other very complicated heat transfer problems that you need to address. So the real question is, how can performance be assessed? And solving this problem brute force, putting all the equations in there to try to solve them, is completely untractable. It cannot be done. So you have to be very intelligent in selecting what are the variables that matter, narrowing the problem to the key components, and eventually putting something that actually can be calculated with certain level of certainty, albeit very, very conservatively, okay? So again, a combustion problem. So one of the ways in which we have substituted combustion is by testing, okay? So we came up with this bridge that says, well, if you cannot model it, test it, okay? Now, tests can be of very different kinds. You can have fundamental tests, like this is a bomb calorimeter, so just the heat of combustion, and that's perfectly fine, okay? We can do heats of combustion of all these materials. We do it with great precision and so forth. Now, when we try to quantify things as spread, then very rapidly we find ourselves stuck to a scenario. Because if you want to test spread rates, there will always be a configuration. So you need to put the theory behind so that you can actually extrapolate the results from the test into reality. And generally, that is not so easy. So in this case, it's a standard test where you have a radiant panel that heats up the material, and they have at an angle so that the heat decays, and you can measure the flame of, in this case, it's lateral spread, as a function of the heat flux that you're providing to the surface, okay? So this particular test, for example, is done for classification, and basically, people try to substitute knowledge with this type of tests, and instead of actually telling you what the spread is, they classify the materials into groups and say, well, this is bad, this is not so bad, this is good, and this is very good. Okay? But these classifications tend to be quite simplistic and many times don't allow for the extrapolation that we need to do. In contrast, we had much more sophisticated tests like TGA, the thermogravimetric analysis or differential scanning calorimetry, that effectively give you, again, certain properties. You can actually construct the chemical kinetics of the pyrolysis process, and that becomes a much more fundamental approach. And that more fundamental approach allows you to get things that enable many times to introduce models that allow for extrapolation. And but the problem is that it's not only a material flammability test, because as we know, we have these composites with non-combustible, combustible, all these things mixed together. So mechanical behavior becomes very, very relevant. Now, one of the things, and this is where you will see me being very, very critical, is we can do all these things, and I'm happy with all these things because they have a fundamental physical basis. The problem happens when those things are not enough. And then what do you do next? You cannot extrapolate. You don't have the tools. You cannot calculate. The system is too complicated. And there's that transition that I tend to find extremely difficult, which is if you don't understand it, burn it big. Okay? Which is basically go and make a big burn, okay, out of this. And this is something that is very prevalent in the fire space, which is these large-scale tests. And all they are is trying to see, what happens, okay? And because it's big, we make the assumption that these tests are giving you information. But generally, all that they're giving you is a lot of uncertainty and very little information. So you're going to see me talking very little about these kinds of things. Because the reality is that we're not truly testing system behavior, we're testing a scenario, and that scenario basically has enormous amount of uncertainty, it's unclear what is really representing, and the problem is the diagnostics are extraordinarily complex. Measuring things in these very, very complex large-scale tests is actually almost impossible. And we have a whole panoply of these tests that basically are there as a surrogate or a substitute to our understanding. Now, in the case of facades, it's a pretty complicated one because we have several tests, and they all tend to appear to represent the same thing. So this is the British version. It's called BS 8481. And basically, you put a wooden crib this is a refractory brick box. It's like a big chimney. And you burn this burn crib, and you let the flame come up. And on the basis of that, you test if it's going to spread or not. Okay? Now, in the US, we have a very similar test, but for practical reasons, instead of a crib, we have a burner. And in this case, we're burning methane and basically using that as the heat source. And we have a very similar criteria of pass and fail in regards to how fast does it take to spread. Now, if you're an insurance company, you might say that this is not the most onerous scenario, and because you're an insurance company, you want to be safer because you're losing money, okay? So FM Global came with an alternative, and they said that actually you have to put two elements of the facade, one in front of each other to get the heat feedback, and they basically put a burner in the bottom and allow the spread to happen when you have the facade elements at both sides. Now, if you look at the heat flux distributions, this is the FM Global test that goes from 120 all the way down to 10 as you move away from the heat source. You have the American test, the NFPA, that basically has almost homogeneous 40 kilowatts per meter squared measured between 2 and 4 meters away from the source. And you have the British test, which makes one single measurement of 75, I think it is, at about 3.5 meters. So here you have 3 parts of the world, or 3 sectors of industry of the world where we have concluded that fire burns differently. So which one is the right one? Are the Americans better than the Brits? You know, or the insurance is the one that actually we should be listening to? And I can take the Australian one, and it's another plot, and another plot, and another plot, because at the end, we will never be able to agree what is the real fire scenario, because the real fire scenario doesn't exist. Depending on the design and the conditions, you will get a different result. And that's a real, real big problem that, as I say, you're not going to hear me saying much good about these very large scale tests. So at the end, you know, is this all we need? Or we really need a better understanding of the combustion problem? And the question is, how much do we need to know to interpret these tests, you know, properly? And you know, ask yourself the question if this is what society wants from you. And the reality is that society wants much more, okay? Because society wants to build tall timber buildings. Society wants to park 1 million Teslas in your underground parking lot filled up with lithium-ion batteries. And, you know, we want to send people to the moon, okay? And we want to have renewable energy with solar panels on top of every one of our buildings. And these very large, you know, oversimplistic representations corresponding to the tests are not sufficient. You know, society wants us to be able to address things like forest fires, and we have to be able to give responses to that. And none of these tests will tell me, you know, how a wild and urban interface fire will actually work. What is the scenario that depicts this? You know, that's a real, you know, very important question. So at the end, to finalize, basically, this is where we are today, you know, and where does the future want us to be. So today, we have this coexistence of rules that are rendered obsolete faster and faster, and with this concept of performance-based design that has to mature to the future. We have strong product regulation, but very weak professional regulation. So if you buy a computer, you will have a UL marking or a CE marking, you know, because we regulate products very heavily, but we don't regulate professionals, so we allow people to permeate from many areas and disciplines into the field. We have this oversimplistic standardized tests that basically privilege simplicity, are very poorly instrumented, but is what dominates the regulatory space. And we need to move away from that, you know, into something that is more consistent with the strong drivers that we exist. So right now, we have very strong economic drivers. Net zero is a massive driver. We have political drivers because our tolerance, you know, to lack of safety is decreasing dramatically. We have increasing impact of new technologies, overall increasing complexity, and it's accelerating. You know, so all these variables are there, and we need to be able to respond. So prescription and standardized solutions are too slow for that. So we have to move, you know, basically into a space in which we're using prescription as a tool, and for that we need the knowledge, you know, to introduce other engineering tools, and basically start regulating the professionals more. So we move towards, you know, basically performance and regulated profession, a very, very strongly regulated profession. So there will always be coexistence between prescription and performance-based approaches, but performance-based approaches should be dominating in the future. And we don't have to have product regulation because that just needs to be verified. So basically the manufacturers should provide the information that we need, but we need to have very strong professional regulation that leads to a professional monopoly, okay? So, and we have to get rid of all this, you know, sort of standardized testings and basically using proper tools of testing to try to come up with the right information that we can extrapolate properly. So basically I'll stop there. There's a few slides at the end that are for you that we will pick up later. I'm not going to cover them because it's an example. So basically I took the example of tall timber buildings and I'm dissecting all the problems in there. But I'll do that tomorrow and the day after, and then you can go back to the example and see how I dissect them. So it's an additional example for you to then reflect on what we do tomorrow and Friday. Okay? So thank you very much, and apologies for running a little bit late. So we'll see you tomorrow.